Welcome to this lecture on the three-phase PWM controller built around the Arduino UNO R4 Wi-Fi and a Python GUI. We will explore how a single low-cost microcontroller board can generate three independent, phase-shifted PWM signals entirely in hardware, and how we can control every parameter of those signals in real time from a desktop application over a simple serial link. The system we will walk through today covers embedded firmware design, hardware timer configuration, serial communication protocol design, and Python GUI architecture, all working together as a complete deployable system. Let us start by understanding what this system actually delivers. We are generating three PWM channels at 20 kHz with a default duty cycle of 50%. The phase offset between channels is adjustable down to 1 degree resolution, giving us fine control over the timing relationship between signals. The most important number on this slide is the CPU load inside loop, minus which is 0. Once the timers are started, the signals run entirely in hardware with no software involvement whatsoever. The guiding principle behind the entire design is this: the Arduino owns the hardware and the GUI is simply a remote control. If the GUI is disconnected, closed, or never opened, the PWM signals continue running at whatever settings were last applied. Now let us look at why the Arduino UNO R4 Wi-Fi is well suited for this application. The board is built around the Renesas RA4M1 microcontroller, which runs at 48 MHz and contains 8 general PWM timer channels, referred to as GPT channels. Each channel is a fully independent hardware counter with its own period register, compare-match register, and output pin control. This is fundamentally different from the older 80 MHz 328p used in the classic UNO, where timers were shared between PWM outputs, the millis, function, and the tone library, creating conflicts and limitations. Here, each GPT channel we claim is dedicated entirely to its PWM output. The pin assignments shown in this table are not guesses. They were verified directly against tables 19.10 and 19.11 in the RA4M1 hardware manual. Pin D3 maps to port 4 pin 2, which with a PSEL value of binary 00011 connects to GTIOC6B on GPT channel 6. D6 maps to GTIOC1A on channel 1, and D9 maps to GTIOC7B on channel 7. All three are on separate channels, which is the essential requirement for independent operation. With the hardware foundation in place, let us now explore how phase shifting is actually implemented. The RA4M1 GPT channels are free-running independent counters. They have no hardware synchronization bus between them. We cannot start all three simultaneously from a single trigger register and expect a phase relationship to emerge. Instead, we use what we call the staggered start method. The mathematics is straightforward. At 20 kHz, the period is 50 microseconds. A 120-degree phase offset corresponds to one-third of that period, which is 16.67 microseconds. A 240-degree offset corresponds to two-thirds, which is 33.33 microseconds. In the firmware, channel A starts first at time 0. We then call delay microseconds for the calculated phase B delay and start channel B. We wait for the remaining time to reach the phase C offset and start channel C. From that point forward, all three timers free run at identical frequencies, and the phase relationship remains stable. The timing diagram at the bottom of the slide shows exactly this. Channel A's rising edge leads, channel B follows after 16.7 microseconds, and channel C follows after 33.3 microseconds. Regarding accuracy, the delay microseconds function on the RA4M1 at 48 MHz has approximately 1 to 2 clock cycle jitter, which translates to around 0.04 microseconds. At 20 kHz, this is less than 0.3 degrees of phase error, more than adequate for motor drive, power electronics and educational applications. Now we will walk through the key design decisions embedded in the firmware itself. Looking at the code, the three PWM out objects are declared globally, each bound to a specific Arduino pin, and by extension, to a specific GPT channel as we verified from the manual. The start_PWM function implements the staggered delay sequence we just discussed. Inside setup, the most critical decision is immediately visible. There is no while serial blocking call. In most Arduino sketches that use serial communication, developers add this line to wait until a USB terminal connects before continuing. Removing it means the board executes start_PWM and produces live PWM output the moment power is applied, with no USB cable, no PC, and no GUI required. The second key decision concerns duty cycle updates. When the user changes duty cycle from the GUI, the firmware calls pulse_perk on each running PWM out object. This function writes directly to the GPT compare match register while the counter is running, updating the duty cycle without stopping the timer, which means no phase disruption and no glitch on the output. Frequency and phase changes, however, require a full stop and restart cycle because they change the fundamental timing of the delays. Finally, the loop function shown at the bottom of this slide contains nothing but serial command passing. The PWM generation is entirely hardware loop, is free to do other work, or in this case, simply wait for instructions. Let us now look at how the firmware and GUI communicate. The protocol operates over USB serial at 115,200 baud using simple new line terminated ASCII commands. Set FREQ followed by a frequency in Hertz changes the output frequency and restarts all timers. Set duty followed by a percentage updates the duty cycle live without any restart. Set PHASEB and set PHASEC set the phase offsets for channels B and C respectively, both requiring a restart since phase is implemented through timing delays. Get status causes the Arduino to reply immediately with its current configuration. Start and stop provide on-demand control of the outputs. Every single command, including set commands, triggers a JSON status response. The JSON payload shown at the bottom of this slide is the common language between the two systems. It carries frequency, duty cycle, both phase values, and a running flag. When the GUI connects to the board for the first time, it sends get status after a short delay, receives this JSON, and uses it to synchronize all of its sliders to exactly what the hardware is currently doing, ensuring the GUI always reflects real hardware state rather than stale default values. With the firmware understood, we will now turn to the Python GUI architecture. The GUI is structured in three clearly separated layers, each with a single responsibility. The first layer is the serial worker class, which owns the PySerial port entirely. It spawns a background daemon thread dedicated to reading incoming data. This is essential because serial read line is a blocking call. If it ran on the main thread, the entire GUI would freeze waiting for data. By moving it to a daemon thread, reading happens continuously in the background. All writes go through a threading.lock to prevent concurrent access corruption. When a line arrives, it fires a callback that uses tkinter self.after mechanism to safely pass the data back to the main thread for processing. The second layer is the visualization layer, consisting of two tkinter canvas subclasses. Phase diagram draws three phasor arrows on a unit circle using polar coordinate geometry, each arrow rotated by its channel's phase angle. Waveform view renders a two-cycle preview of all three waveforms simultaneously. It uses a single elegant mathematical technique, subtracting the phase fraction from the time variable and applying modulo 1.0, correctly handles all phase values including wraparound cases. Both canvases redraw automatically whenever any slider moves. The third layer is the app class itself, the control layer. It owns all the tk state variables, dispatches serial commands when sliders change, passes incoming JSON from the Arduino, and keeps the GUI synchronized with the hardware at all times. We can now summarize the 8 design principles that shaped every decision in this project. Hardware first means the GPT timers run autonomously with zero CPU involvement in loop. GUI optional means the board produces output on power up regardless of whether a PC is connected. Verified pins means every pin-to-channel assignment was cross-referenced against the RA4M1 hardware manual rather than assumed. Live duty means pulse_perk updates the running timer without a restart or glitch. Thread-safe serial means a daemon thread, a lock, and self.after together prevent race conditions and GUI freezes. State sync means the Arduino replies with full JSON after every command, so the GUI never shows stale values. One dependency means the Python GUI requires only PySerial. Everything else is Python standard library, so setup is a single pip install. And the preset system means common configurations like 3-phase 120 degrees, 90 degrees, in-phase and half-bridge are available as one-click buttons that set all parameters simultaneously. Together, these principles produce a system that is reliable, deployable, and straightforward to demonstrate. Let us now consider where a system like this would actually be used in practice. The most direct application is 3-phase motor drives, where the gate signals for a 3-phase inverter bridge need to be phase shifted by 120 degrees to create the rotating magnetic field that drives BLDC and induction motors. Interleaved DC-DC converters use phase-shifted switching across multiple converter stages to reduce input and output ripple current, improving efficiency and reducing filter component size. Multi-phase battery chargers for electric vehicles and energy storage systems apply the same principle to balance charging current across phases. Class D audio amplifiers require ultra-low jitter gate drive signals at frequencies above 20 kHz, where even small timing errors translate directly into harmonic distortion. As a configurable lab signal generator, this system provides a quick and inexpensive way to generate multi-channel PWM stimuli for testing and characterizing power electronic circuits. And in an educational context, the combination of the phase diagram, the live waveform preview, and the real-time adjustable sliders makes phase relationships, duty cycles, and switching behavior immediately visible and tangible for students. To bring everything together, we have built a system that generates 3 independent 20 kHz PWM signals from a single Arduino UNO R4 Wi-Fi board, phase-shifted by configurable degrees, and controllable in real time from a Python GUI over serial. The signals are produced by dedicated GPT hardware timers, so the CPU is completely free. Duty cycle updates are glitch-free through direct register writes, while frequency and phase changes execute a clean stop and restart cycle. The board works standalone without any USB connection, and when the GUI does connect, it automatically synchronizes its sliders to the current hardware state through the JSON protocol. The entire project lives in 2 files. PWM_final.ino for the Arduino firmware, and PWM_GUI.py for the Python GUI, with a single pip install PySerial as the only external dependency. The codes are in Git but game by Kitais. The link is shared in description. Thank you for watching this video. Like and subscribe for more.